Section 2.4 is introducing biconditional statements and definitions. A biconditional statement is a statement that can be written in the form of P if and only if Q. So this means if P then Q and if Q then P. So it's a combination of a conditional statement and its converse. So the conditional was if P then Q. The converse is flipping those around and saying if Q then P. So for example 1, it says write a conditional statement and converse within each biconditional statement. So our first one given here is two angles are congruent if and only if their measures are equal. So the first part, two angles are congruent, is the P. And then if and only if, so that tells us it's a biconditional. Their measures are equal, and that's our Q. So for our conditional statement that we have to write, the conditional statement is if P, then Q. So we're going to have to say if two angles are congruent, then their measures are equal. And then we have to write the converse. And the converse is simply flipping those around. If Q, then P. So we would say if their measures are equal, then two angles are congruent. So we were given a biconditional, we had to pull it apart and write the conditional and converse. So the same thing goes for part B here. A solution is a base if and only if. So those arrows, that's another way of writing if and only if. It has a pH greater than 7. So the first part is the P. The second part is the Q. So for the conditional, we have to write if a solution is a base, then it has a pH greater than 7. And for the converse, we flip those. We'll say if Q, then P. So if a solution has a pH greater than 7, then it is a base. For example 2, for each conditional statement, write the converse and a biconditional statement. So now they're giving the conditional, we have to write a converse. So the converse is just flipping them. So this one says if 2x plus 5 equals 11, then x equals 3. So we're going to flip them around. So we're going to say if x equals 3, then 2x plus 5 equals 11. Then we have to do the biconditional statement. could be taking the p-value and writing if and only if after that and before the q. So we are going to say 2x plus 5 equals 11 if and only if x equals 3. So down here, this one says if a point is a midpoint, then it divides the segment into two congruent segments. So the if is the p, and the then is the q. So for it, this is the conditional, we have to write the converse. And so we flip it. If the point divides the segment into two congruent segments, then it is a midpoint. And for our biconditional statement, we're going to go back up and leave it in the same order, the P and then the Q, but we're going to change it to if and only if in the middle. So a point is a midpoint. And remember, we can use the line with the arrows. For if and only if, it divides the segment into two congruent segments. For a biconditional statement to be true, both the conditional statement and its converse must be true. If either the conditional statement or the converse is false, then the biconditional statement is false. So both have to be true in order for it to be true, for the biconditional statement to be true. If one is false, then the biconditional is false. So moving on to example 3, determine if each biconditional is true. If false, give a counterexample. So our first one says a square has a side length of 5 if and only if it has an area of 25. To write the conditional, and the converse. So the conditional, we have to make if a square has a side length of 5, then it has an area of 25. So let's see if that's true. If a square has a side length of 5, then it has an area of 25. That would be true because the square has the same side lengths. So we would have to do 5 times 5 to get the area, which would be 25. So that is true. Then we have to write the converse. So we have to flip. We're going to say if the square has an area of 25, then it has a side length of 5. So if it has an area of 25, then its side length has to be 5. Well, that's true because in order to find the side length, if you know the area, you take the square root. So the square root of 25 is 5. So this is true as well. So the biconditional statement is true. And then for part B, the number n is a positive integer if and only if 2n is a natural number. So conditional would be if the number is n is positive, then 2n is a natural number. So let's see if that is true. If the number n is a positive integer, then 2 times that number is a natural number. Well, if we plugged in 5, 2 times 5 would be 10. That's a natural number. Remember, natural numbers are counting numbers. So whole numbers, positive whole numbers, 1 through whatever for infinity. So no matter what I plug in, as long as it has to be a positive integer, so 2 times 10 would be 20, that would work. So yes, this is true. Then we have to write the converse. And flip this around. If 2n is a natural number, then the number n is a positive integer. So is that true? Think about this one for a second here. If 2n is a natural number, so let's say 2n equals 1. If I solve for n, I would have to divide both sides by 2, so n would be 1/2. This says that the number n is a positive integer. 1/2 is not a positive integer. 1/2 is a rational number, not an integer. So this one would be false. So therefore, the biconditional statement is false. All right, definition is a statement that describes a mathematical object and can be written as a true biconditional. So we have to turn the definition given into a biconditional. So for this one, a triangle is a 3-sided polygon. We can say a figure is a triangle if and only if it is a 3-sided polygon. And then for part B, a segment bisector is a ray, segment, or line that divides a segment into 2 congruent segments. So this is a definition of a segment bisector. So we can say a ray, segment, or line is a segment bisector if and only if it divides a segment into 2 congruent segments. So you're just rewriting the definition with if and only if in the middle.